right, so this is the first little mini lecture on video that you will have for chapter 24 for Thursday while I am away. So in chapter 24, we're going to start to get into the idea of circuits. So we're starting to see elements that can be put in a circuit, where we have items connected by wires and batteries and so on. But we're not quite there, but we're sort of there. We're starting to talk about the idea of capacitance, and related to that, which we will talk about next lecture, will be dielectrics. So in this chapter, one of the first things we're going to do is learn what the heck do we mean by a capacitor, and how do we calculate that? Because what capacitors do, as we'll learn about them, is they store charge, and they store charge that's separated. So they take positive charge and negative charge, and they're separated. And if you think about what you've learned so far in electrostatics, that separation of charge means that there's going to be an electric field between the charges, which also means there's going to be a potential difference between those two charges. And so we start to get into exactly what a capacitor is. Once we learn a little bit about capacitors, we're going to think about how we can connect them together in different ways, and how charge is distributed among capacitors when they're connected. And we'll learn terms that we'll use later, like connected in parallel and connected in series, and understand what that means. We're also going to talk about how capacitors store energy, because in a sense, I feel like that's one of the ways to really view a capacitor, is that it is this element in a circuit where, by virtue of having charge separated on two conductors, it's really storing energy within that electric field that is set up between the conductors. And so we'll talk about how to quantify that energy and what things affect it. Finally, we're going to talk about dielectrics, which are materials that are placed between the conductors and a capacitor, and why we would do that. So those are sort of the previews of the things that we're going to be looking at in this chapter. So I just wanted to give some examples of situations where a capacitor would be used. For instance, in flash photography, when you make that flash, when you turn that light, illuminate it, that energy is coming from energy stored in a capacitor. And when it's released, we can light up our flash. Sorry, I keep doing the wrong button. Other examples are the Defib Reader. Okay, I'm sorry if I said that wrong, but I have a hard time saying that word. So the paddles that they use on TV shows, or otherwise they do use them in real life, where they shock a person's heart to bring it back into a normal rhythm. Even thinking about when we were watching that happening not in real life, like on a TV show, and they'll talk about charging. They are charging up those paddles, so they're charging up the capacitors that are storing the charge, and then when they shock the person, they're going to release that charge and send electrical current through their heart to bring it into a normal rhythm. And then we have a much more mundane example of intermittent windshield wipers, when you can have them go off like every so few seconds. That's an example of what we're going to learn about in a little bit, like later on, an RC circuit. And so that's another use of them. So now we're going to get to know exactly what a capacitor is. Now, this is a really general picture, and this is not like what we would put into a circuit, but this is more a general description of what a capacitor is. In a capacitor, we have two conductors, and so here we have conductor A and conductor B mentioned here, and they're separated, usually either separated by a vacuum or by an insulator. Later on, we'll talk about that. That's a dielectric. And so that's sort of what the setup of the capacitor is. It's not actually going to be a blob of a conductor. There are different ways to make it. And we'll talk about one example in a little bit called the parallel plate capacitor. When we charge up a capacitor, what we actually are doing is we put a positive charge on one conductor and a negative charge on the other. The magnitude of charge on each conductor is the same. It's just that they have opposite signs. So in a way, we would say that the total charge on the capacitor at that time is 0, because of course the charges would cancel out. But typically we would just say that the charge on the capacitor would be given by Q, even though to sort of represent the magnitude of the charge on each conductor. So we learned, and we see in this picture, that because there's this positive charge and negative charge and they're separated by some distance, you know that that's going to create an electric field between the two conductors. And here you see the electric field lines being drawn. But we also learned in the last chapter that if you move along an electric field, there is going to be a potential difference. And so just to remind you, we learned that delta V would be equal to minus the integral of E dot ds. And remember that what that negative sign refers to is that as we're moving in the direction of the electric field, we're moving to a location of decreasing potential. And so in a way, what we could think of is that up at the positive conductor, the positively charged conductor, we're at a higher potential, and at the lower potential is found at the negative charge. A lot of times when we're going to be using this relationship, it's taken for granted that we understand sort of in an electric field where the higher potential is and where the lower potential is. And also, if we have a constant electric field, we might just sort of go with this relationship that the change in potential in an electric field as we travel some distance in the electric field could just be given by this. Keep in mind that here we're not worrying about the negative sign because we're not so worried about the direction. This is sort of, when we know where the higher potential is in the electric field. Then we drop the negative sign just to make it a little simpler. Hopefully that's not confusing. So, all right, so far we have this capacitor. It's two conductors. They have an equal and opposite charge stored on them. This creates an electric field between the conductors and also a potential difference across the conductors. And another thing that we talk about that is happening in the capacitor, which it might not be obvious to us at first, but we'll gradually start to talk about it in more detail, is the idea that storing the charge in the way we do in a capacitor also means that we're storing energy in the capacitor. And the idea is that that energy can be used if we discharge the capacitor. So if we suddenly allowed the charge to move, perhaps we know that the negative and the positive charges want to be together. So if they somehow were able to equalize, there would be a sudden release of energy by the flow of that charge. Normally, the way that we think about the storage of energy is that we say that it's stored in this electric field that exists between the conductors. So one of the ways that we can charge a capacitor is that we can take the two conductors and connect them to a battery. So if we sort of imagine a battery, and it has two terminals, a positive terminal and a negative terminal. And so that's sort of, we're going to draw this in a way that we never will in a real picture, a real circuit diagram, but just to sort of give you a visual for what we're talking about here. So this is our capacitor. I am using sort of a mixture of symbols here because the picture of my battery is just, I'm trying to show you more of a realistic picture of what a battery might look like. But this symbol of two parallel lines of equal length is actually how we do show a capacitor if we're drawing it in a circuit diagram, which we'll be doing more of as we continue with this chapter and later chapters. So you probably know that batteries are labeled like for instance, they might be a 9-volt battery. And so by connecting the terminals of the battery to the two different conductors of the capacitor, what's going to happen is that we're going to have, this conductor is going to acquire a positive charge, and this conductor is going to acquire a negative charge. Because what's going to happen is the battery is going to give and the wires connecting to the capacitor will allow the charges to move the way that they want to. And so electrons are going to start to move around, and they will leave this terminal and will travel around and get onto this, well, not the terminal, but that conductor. And so we'll end up with a net positive charge on one plate and a negative charge on the other plate. And now you can maybe see why, for the capacitor, this will have the same magnitude of charge on each plate, because it's really caused by, electrons moving one by one from one plate to the other. So what happens is then the potential difference across the plates of the capacitor would have to be the same as the potential difference of the battery. And the reason that happens is because basically until the potential difference across the conductors in the capacitor do have the same potential difference as the battery does, until that happens, charge will continue to move. Once the potential difference across the plates of the capacitor are the same as the ones across the terminals of the battery, then there's no impetus for the charges to continue moving. Then they'll just stop transferring and they'll stay there. And so that's sort of how the capacitor will become charged. And so in a sense here, if we call VAB, if we say this is A and this is B of the battery, is going to be equal to 9 volts here. This is for the capacitor. And so that's how it gets that potential difference and how it gets charged up. And then, of course, because they have that charge, because on one plate there's a positive charge, and in another plate there's a negative charge, this is going to create an electric field, and then, of course, that's why there's a potential difference across the two plates. Now, finally, we're going to talk about, a way that we define capacitance. And so this is a definition that we don't want to forget. This is a relationship that's really important. So for a particular capacitor, when we describe it, we'll say it has a certain capacitance, which is denoted by C, right here. And it's the ratio of the charge on each conductor. And keep in mind, it's not the total charge, but it's the magnitude of charge on each conductor, divided by the potential difference between the conductors when they're fully charged. And so that ratio is how we define the capacitance of a capacitor. It's labeled in a unit called a farad, which would be 1 coulomb per volt. A farad is huge. You don't actually make capacitors that have a capacitance of like 2 farads or anything like that. More often than that, they're going to be something like a microfarad. Here you see that little term mu, that's the Greek letter mu. It might look like the coefficient of friction, it was the same symbol, but here it represents 10 to the minus 6. So when I see, for instance, 2 microfarads for a capacitor, it means that it has 2 times 10 to the minus 6 farad capacitance. We're going to see some prefixes that when we're talking about capacitance, and you are responsible to know what those are. And so, for instance, you might see nanofarads or picofarads, etc. And so you want to become familiar with what those mean in terms of the exponent. Now, one of the things that is really important to remember is that, when you see this expression that capacitance is charge over potential difference, you might be tempted to think that we could take a capacitor and it would have any capacitance that we wanted. All we would have to do would be to manipulate the charge and the voltage, right? It seems like that would be possible. But it turns out that that's not true. When you construct a capacitor, and there are different ways of making them, one of which that we'll use often, and the way we visualize it, is 2 parallel conductors, and so that's called a parallel plate conductor, capacitor. But anyway, when we make a capacitor, we construct it so that it will have a particular capacitance. And that capacitance will then determine what the ratio of charge to potential difference that capacitor can have. So this is basically a constant for a given capacitor. And the ratio of these two quantities always will have to be equal to the value of C. So for instance, if you have a capacitance of, let's say, 2 microfarads, and then if you had a potential difference of 1 volt, that means that that capacitor can only store a charge of 2 microcoulombs, okay? You can't put any amount of charge on that for a given potential difference. The ratio always has to be equal to this. All right, so as I just said a minute ago, there are different ways to construct a capacitor, and one of the most popular ones that we talk about is a parallel plate capacitor. And basically it's made up of 2 plates. The plates are going to be conducting material. They are parallel to each other, and they have some cross-sectional area and also some plate separation. And because of that plate separation, they have a potential difference of VAB. Well, it turns out that if we think about the expression for capacitance, we can actually come up with another expression for capacitance that is specific to parallel plate capacitors and has a relationship to how they're constructed. So let's take a look at that. So we start off with the idea that the capacitance is equal to the charge over the voltage. And of course we're talking about parallel plate. So one of the first things I could do is I could say, well, the potential difference across the plates is going to be given by the electric field times the distance. And then we could say that, okay, well, because it's a conducting plate, I learned that the electric field of a conducting plate is sigma over epsilon naught. And so this is D and this is Q. And I'm just going to put my epsilon naught on top because I don't like fractions in my denominator. And then I'm going to remember that the definition of charge, sigma here, was charge per unit area. So I'm going to substitute that in to my expression here. And again, I don't like fractions in my denominator. Notice my Q's cancel out. And I'm left with this expression. This becomes my expression for the capacitance of a parallel plate capacitor. And so this is the area of the plates. And this is the separation between the plates. And this is another way that we can calculate capacitance. We can also remember that while this is specific for parallel plate capacitors, it will also be true that the capacitance is the ratio of charge to voltage, which sometimes we can use sort of these two things together to figure stuff out. And there we are. One of the things about this expression is that you see that the capacitance in this expression is depending on the geometry of the capacitor. There are actually other expressions for different ways of making capacitors that have similar expressions. For instance, you can make a capacitor by two spherical shells, one inside of each other, or similarly, you could make a capacitor by two cylinders, one that lies inside of each other. And in both cases, we can come up with an expression for the capacitance and how it depends on the geometry of how they're constructed. This kind of goes back to the statement I made a few slides ago that the capacitance of a capacitor is purely based on how it's constructed. And here you see, here's an example when we look at this expression. It is based on how we put together the parallel plate capacitor, how big we made the plates, how far apart we put them, etc. If you looked at expressions for a spherical capacitor or a cylindrical capacitor, you would see that the same thing was true, that it was going to be related to the physical size of the components. All right, and so that is it for today. So what I've done is I do have another little video for you to watch. It actually was made a few years ago, but it is still relevant because it's for the same material. And in that video, you will see how to add or how to deal with capacitors that are connected in different ways and how to simplify them. And then finally, I'm going to give you a couple questions like we would have had during class for you to look at after you've watched the video, and I will be asking you to complete those and turn them in the next time that we meet. So I hope you enjoyed a little respite from physics, but of course you don't really get a respite because you still have to be learning this material. And I will see you next Monday.